We've completed our discussion on potential flow and are now going to discuss some viscous flows. We're going to assume still that our bodies are relatively streamlined and at moderate angles of attack so that there's no significant separation. In other words, we're going to introduce boundary layers into the flow field to modify, still using what we did in potential flow, but now being able to modify it with a thin layer where viscosity is important. Again, assuming that there isn't a large wake that would violate our assumptions of potential flow everywhere outside of this boundary layer. So for today, we're going to just go through some concepts, not really any math today, just some preliminaries on boundary layers. Hopefully much of this will be review, and then next week we'll start getting into some of the math of boundary layer theory. So here's just a picture of some elements in a boundary layer. Often always, right, the Reynolds number at the beginning is very low. So it'll start out laminar, that may be very short-lived. At some point it will transition usually to turbulent flow. And then there may be separation. And separation could hopefully occurs very near the trailing edge of our geometry, but it could occur at any point. In fact, it can occur in the laminar region. Sometimes, in fact, when it occurs in the laminar region, say here at this high angle of attack, we could get separation early on, and the flow, if it's so early, can even reattach sometimes. This is called a laminar separation bubble. But that's a less common scenario. We'll notice from this figure the presence of two types of drag. So in potential flow theory, we could predict our forces and moments reasonably well, with the exception of drag. We get lift. In 3D, we can even get a side force, and we can get all three moments, pitching, yaw, and rolling moments, pretty well, as long, again, as we don't have big separation of wakes. Or separated flows. A wake is actually okay, as we'll see as we talk about lifting body soon, but separation is the problem. So as long as we don't have that, you get all those things pretty well, except for drag. And if you recall, for potential flow, the drag is always zero, which of course is not right. So a few things have changed now. Our boundary condition is going to be different. No longer is it flow tangency. We could still say flow tangency outside of the boundary layer, but at the surface, we have the no slip condition. So both the normal and the tangential velocity go to zero. From this picture, we notice two types of drag. One is a pressure drag. These are names we'll give to it, or profile drag, I guess is a better name. And this is due to the momentum deficit. So if we look here up at the free stream flow is all uniform. If at the back edge it was also of the same magnitude uniform, there would be no drag. But because we have this deficit here, some momentum has been lost, energy has been taken out of the fluid, there must be a drag. Conversely, if there was an increase in velocity, we would know that we had a thrust producing device upstream, right? So there's this profile drag. The other component here is the skin friction drag. So the fluid rubbing over this surface here creates drag, which we call skin friction. Of course, drag is drag, it's a force. These are just convenient ways we compartmentalize them because of the primary drivers in them, right? So the skin friction drag is primarily driven by the surface roughness, my wetted area, the area that the fluid passes over, and so on. Whereas this profile drag, as the name suggests, it's primarily driven by the shape, right? A streamlined shape will have a smaller wake, smaller profile drag. So again, hopefully by way of review, this is just a picture of the laminar and the turbulent region. Important to note, important distinction here is that a turbulent boundary layer has a higher velocity near the wall. So if we think about, let's think about some of the reasons why this occurs, and also some of the engineering implications. The laminar boundary layer refers to layers, so we could think of it conceptually as separate layers of fluid, each passing somewhat independently, right? Slower and then faster and faster as we get further away. That, of course, isn't a perfect image. There is some mixing, but it's a relatively small amount of mixing, and so most of the mixing that occurs is at the molecular level, as we've discussed previously. So really small scale mixing. Turbulent flow, on the other hand, right, has large scale mixing, unsteady mixing, many scales. So there's, a lot of mixing with the high speed flow up top, the low speed below. So what that means is that this turbulent boundary layer, because it's bringing in energy from these higher layers, there's actually a higher velocity near the wall than the laminar case. That leads to two things. One is, if we recall, that the skin friction or the shear stress is proportional to velocity gradients, right? And so specifically, my shear stress at the wall, which I care about for drag, that's going to be my skin friction drag, is going to be the velocity gradient at the wall. And the turbulent boundary layer has a steeper slope as compared to the laminar. And steeper, if we're, it's maybe not quite intuitive. This doesn't look steeper from how we're used to looking at, but remember, this is my U is the numerator here, Y is the denominator. So it's kind of flipped from how we would normally imagine slope or a derivative and thinking about slope. But in other words, for a given change in Y in height, right, this velocity is bigger, right? So if I go to the same height, the turbulent velocity is bigger. So this is a bigger slope. The turbulent velocity has a bigger slope and thus a higher shear stress, meaning more skin friction drag. So all else equal, a turbulent boundary layer will produce more skin friction drag. This is why in many applications, as we're trying to reduce drag, we push for more laminar flow. You often hear, or see many papers or studies on trying to promote natural laminar flow and preserve a longer region of laminar flow to reduce drag. However, that's not the only story, right? We talked about these kind of two components of drag, the skin friction drag and the profile drag. Well, for profile drag, it often actually helps to have turbulent flow for the same reason, that because there is greater velocity near the surface. So if we go back and think, this is easier to visualize with a blunt body like a sphere, but same principle applies in general. As the fluid comes around, as we've discussed, we come across an adverse pressure gradient. We have a very low pressure on top and a higher towards the bottom. So we're moving in against the pressure, and the flow is going to want to separate, or it's going to be slowing down in that adverse pressure gradient. So particularly here in the boundary layer, it's going to be slowing down, and eventually we'll have no flow, no velocity in this streamwise direction. So it'll separate, leave the body. A turbulent boundary layer has more momentum near the base, also because of the mixing. It's being able to bring in more energy back in towards the body, and so it can it will delay separation. So for turbulent boundary layer, I guess I should draw it in red. Oops, just to match what I've done here. So let's say a laminar boundary layer doesn't have as much momentum. It's going to separate relatively early here, right? This comes around. Whereas the turbulent boundary layer, because it has more momentum, can come around further and have a smaller wake that leads to less profile drag. So we kind of have this trade-off of the turbulence. Our turbulent boundary layer, we have more skin friction drag, but potentially we will have less profile drag. And those trade-offs kind of depend on the shape and my application, the flow conditions. But in general, let's say for an airplane, we would like to have laminar flow, especially near the leading edge, but we just don't want to take that too far. Maybe 30% laminar flow or so, but if we go too far, then that may limit the types of angle attacks we can go to. If we're at a very modest angle of attack, we could have laminar flow quite extensively, but we won't be very robust. As we increase angle of attack and we need to navigate a more adverse pressure gradient, we would like to have turbulent flow at this point so that we can navigate that pressure gradient without separating, so that we can maintain higher degrees of angle of attack. So that's why we don't actually want 100% laminar flow. We do want a decent amount, but not to go too extreme. And there are many mechanisms for that. Sometimes you'll see on an airplane, we may discuss some of these later, but different devices that can be used to induce turbulence so that you can maintain, especially at say a landing condition, when you're at a slower speed and you have a higher angle of attack, you want to make sure that you have turbulent flow to delay that separation and the consequently high drag, and for an airplane, the big loss of lift, which is perhaps even more problematic, which we call stall. The other thing we'll notice from this picture is that the laminar boundary layer recovers to what we call our edge velocity much quicker than the turbulent boundary layer. In other words, the turbulent boundary layer is much thicker. Because of that large scale mixing, its effects extend further out into the flow field. Just real quick, I should define this edge velocity. So we'll use this a few times. Rather than a free stream velocity, the idea is that a boundary layer is such a localized thing that if I really greatly exaggerate the scale here, say this is my boundary layer, and so here's a picture of this greatly exaggerated boundary layer, the velocity just here, just on the outside of the boundary layer, we'd call the edge velocity. So this is not a constant along the airfoil, but this is what we might compute, for example, in our potential flow theory, the velocity just outside the boundary layer. And again, this boundary layer is very tiny, so it's going to be very close to the actual geometry. But it's not V infinity, it's just the local velocity here. So I actually already just defined this, right? The wall shear stress. Shear stress, of course, is again defined everywhere, but the wall, which we typically care about for drag, is defined at y = 0. And for a boundary layer, we'll often use, sometimes other coordinates are used, but we'll typically use x, not as a global x, but just as a local coordinate, meaning it was going to follow the boundary layer. So it's going to curve around geometry, and y will always be normal to the surface. So y = 0 is just right at the surface. The skin friction coefficient is just a normalization, right? So this is called the skin friction coefficient. It's just a normalized version of my shear stress. And I should say this is really the local skin friction coefficient. Sometimes we use a total one as well, but this is just my shear stress, and it could be normalized one of two ways. Sometimes we normalize by free stream conditions, but often, especially when we're doing boundary layer quantities, we would normalize it with the edge velocity, that velocity that's just outside of the boundary layer. This is V sub E. Okay, so let's discuss transition. There's a video I show in class, but I'm not going to show it here in this video. It's recording, but you might look at, here's a link, but you might look to any video on transition. In this particular video, I'll just kind of illustrate what's going to happen, is that if you were to inject a dye in a fluid and just watch it and increase the speed of the fluid, initially, right, it would just kind of just go straight as it's very slow. And as you increase the speed, you might see some small wobbles, but the dye would be very coherent. As we increase the speed more, right, then you might see this start to breaking up, and you might see a little bit of mist from the dye as it's mixing. And then eventually it's just a big mist of the dye. It's being very well mixed in its turbulent flow. So as you increase the speed, you'll kind of see this behavior occurring. And transition, and the reason why I see this is that transition is all about instabilities. So if the flow field were perfectly smooth, there was no variation, right? Everything was perfectly smooth around it. Geometry, there's no disturbances, which of course never happens, and things would just continue perfectly. But of course there are disturbances, right? There's, some wind or some other current or whatever, just some small disturbance, a little bump in a wall nearby, slight breeze, any sort of tiny disturbance is going to cause the fluid to be perturbed a little bit. Now, if I'm at low Reynolds numbers, then that means that my viscous forces are high relative to my inertial forces. So those instabilities get damped out, right? So the viscosity is going to damp those disturbances, and so they won't grow. You'll see a little wiggle, but these disturbances don't grow. Conversely, at high Reynolds numbers, then any instability gets amplified and it grows quickly. So the inertial forces are very large compared to the viscous forces, so the damping is too weak, and an instability just grows, and this leads to turbulent flow. So just like turbulence is, chaotic, the prediction of transition is somewhat as well because it's driven by turbulence. So while we'll often predict turbulence or transition at a point, we should realize that transition doesn't occur at a point, but really kind of occurs over a region as we transition from the laminar kind of predictable behavior to this chaotic turbulent flow where instabilities are being magnified. Okay, so what are some of the factors that affect transition? These are things we want to understand as engineers, because as we discussed, we want to preserve laminar flow often over much of our geometry and then have turbulent flow later. So if we can delay a turbulence, if it's coming too early and we can have a little more laminar flow, we can reduce our drag. So we understand some of these effects. Probably the big three are surface roughness. And that's why, of course, you'll see in many aerospace applications and in other things like performance race cars or sailboats, right? We get very smooth surfaces so that we can reduce that skin friction drag and promote laminar flow for a longer period. Another is going to be the free stream conditions. And really, maybe I should say upstream, because if we may have multiple bodies, but the upstream turbulence. So if upstream, we have a lot of disturbances already, then we're going to be transitioning quicker, right? So sort of the noise, the instabilities that already exist upstream are obviously going to affect how quickly we transition. The other big one is the pressure gradient. So that's, of course, influenced by the geometry and the flow conditions. But for a given geometry, I could change my pressure gradient. Even with a very small, a slight adverse pressure gradient, we typically are going to have transition, which is why on an airfoil, it's hard to have extensive laminar flow because most of my favorable pressure gradient occurs very near the front of the airfoil. And then as I come back, I'm moving across this adverse pressure gradient. And so it's very easy to transition at that point. Or in other words, it's hard to maintain laminar flow for much longer. Again, we call the adverse pressure gradient as I'm moving from the low to the high pressure. This requires extra work and is going to amplify these instabilities causing transition. The other two that are less common because they're usually less naturally occurring, but these are heat transfer and suction or blowing, sort of actively sucking up the boundary layer or injecting momentum into the boundary layer. These things can also affect my transition. So in the case of heat transfer, for example, we could use cooling. We could add cooling elements on a wing, for example, and that can tend to stabilize the boundary layer, delaying transition. Suction and blowing, similar ideas to where you might have a little port, right? And as the boundary layer develops, you could suck it in and kind of a new one will develop. So we've delayed transition, or we could have a port where we inject momentum into the fluid so that we may try to keep it attached longer or to keep it in the laminar region longer. Both of these cases, as I said, are usually not occurring naturally. We have to impart some energy either for cooling or suction or whatever. And so whether it's worth it or not is hard to say. Often it's not because we have to expend some energy, but if we can do it in an efficient way, then it may, there are certainly applications where it's worth it. Sometimes one example is in like a quiet supersonic wind tunnel where, this is not flying, where we want to suck the boundary layers off the wall so that they're not affecting, the test article in the middle. So I mentioned this already, but a picture might be more helpful. We talked about how separation occurs as the velocity near the wall decreases. So if we are looking at a boundary layer profile, the turbulent boundary layer or the laminar, whichever case, near the wall is being slowed down, right? Because in this case, say I'm moving in an adverse pressure gradient. So there's a pressure moving against me. So my profile wants to slow down. Well, these velocities near the wall have less momentum, they're more affected, and they're spending more time in that adverse pressure gradient, so they're going to slow down. And eventually, near the wall, the velocity is zero. Sorry, So I actually have no forward momentum in the x direction. And by definition, that's separation, right? Because I'm no longer moving along the body. The only component of velocity I would have in this case is a small upward component. So the fluid is going to leave the body and recirculate around, filling that void, and I'm going to have this wake. Okay, this also, by the way, if we recall shear stress, remember it's this. This also is another way that we can recognize where separation occurs if we're looking at some data or numerical simulation. Notice that at separation, the slope here is 0. And so at separation, the shear stress, wall shear stress will be 0. That's another indication of separation. Separation, as we can see, again, leads to this big drag, decrease in lift if we're talking about lifting body. Conversely here, right, there's an adverse. We could put a favorable pressure gradient that can actually stabilize the boundary layer, right? And that's why near the nose, we're not going to have separation, right? We can have a very extreme angle of attack and kind of navigate that, but then on the back, as soon as we hit that adverse pressure gradient, we might be prone to separate if we're getting too aggressive. This also explains why these aerodynamic vehicles will have fairings. Here's a classic example. If I have a fuselage and I have a wing, let's say joining up right against the fuselage. If I have no fairing, let's say I drew that. So here's the side of the wing and here's my fuselage. So I'm looking right at the section where the fuselage just intersects with the wing and I have no fairing. So this is just a straight edge. Well, in that case, I have a stagnation point right here. Right, and if that's a stagnation point, that's not a problem if I'm, outside here of the wing, away from the fuselage, because this is for the wing at least in a very favorable region, so it'll accelerate over no separation. But if I'm looking at the fluid passing along this fuselage, this is not in a favorable gradient. It's just moving here alongside the fuselage, and then I hit this stagnation point. Well, by definition, then I'm going to separate, right? Because I don't have any favorable gradient anymore. I have no more forward velocity. And so it's going to cause some separation on the fuselage. So you'll notice that there'll be a complex fairing, right? Kind of a gradual transition so that the flow does not stop here. It will accelerate, kind of curve onto the wing. Same with like a winglet on a wing, right? We'll see kind of these, not just a straight edge, but some complex fairings. Okay, so just briefly want to remind you about, this is the same idea we're just discussing earlier. I'm sure you've all seen this, the drag of a sphere, and often, we hear these analogies or explanations of this behavior, like say for a golf ball, why does it have a dimpled surface? Well, this figure helps explain it, as we've seen that a laminar boundary layer is going to separate pretty early, right? Whereas a turbulent boundary layer, because of that momentum near the surface, can extend further and delay separation. And so for a blunt body like a sphere, that means as I go from the laminar and then into turbulent, I can get this big drop in drag because of the profile drag. And so for a golf ball, it's just such the case that the Reynolds number that we hit in is somewhere over here, where where a smooth ball would still be in a laminar region and have a lot of drag. However, if we intentionally introduce roughness right on the golf ball with these dimples, then we can induce turbulence, and so transition will occur earlier, and so we can be in a turbulent regime and reduce our drag, be able to hit a golf ball further. A few other implications. I guess I'll say this one first real quick, which we've seen before. Potential flow theory, right? We're going to predict this curve here. It's going to be perfectly straight. In fact, the slope might not actually be exactly the same either. We saw a slope of 2 pi, and I'm exaggerating a little bit, but viscosity tends to reduce that lift curve slope. That is generally not super significant, usually very minor, but of course the big one is, as we get to towards separation, then there's going to be a massive drop in lift, which we call stall. One thing to keep in mind, and we'll bring this up again later as we start to couple what we're doing now with panel codes, is that the presence of the boundary layer has changed what we could call the effective body. Because I have this boundary layer that's slowing the fluid down, it's kind of like I've made my body bigger, right? A bigger body would also have less mass and momentum flow around it. And so it's not exactly the size of the boundary layers we've discussed. We'll talk next week about some different ways to measure boundary layer thickness related exactly to this idea. But because there's some slowing down, we're extracting or losing some mass momentum in that boundary layer, effectively we've made a thicker body. And this is one way, as we'll see, that we can use a panel code where we may have to iterate or couple these codes where if we solve the potential flow theory over the actual body and then compute a boundary layer, we may need to go back and change the body because it's now effectively a different shape because of the presence of the boundary layer. So we could recompute that pressure distribution. Finally, just want to leave you with one kind of interesting thought here. This is a picture of a baseball, but I just want to use it to motivate this idea. So if you go on YouTube, you can find a lot of videos of example one is you take a ball and you spin it, right? Just kind of spin it and throw it off a high place. Like, so there's a video out there of throwing a basketball off of a dam. And because of that spin, you'll see it go shooting off really far away, right? So if you've ever played tennis, for example, you've seen that if you put a spin on it, in this case, let's say it's spinning this way. Of course, this is my free stream, which means I'm hitting it from right to left. And I put a little bit of an underspin, that creates a bit of lift, right? So in other words, it kind of keeps the ball moving in a relatively flat trajectory, or opposite, if I put a top spin over it, right? If I get over it, then that creates a force downwards and the ball goes shooting down to the ground faster than normal, okay? So the way this is typically explained and is also in these videos is a Magnus effect, meaning that this velocity is, or since this ball is rotating, it kind of accelerates the fluid over the top and slows it down here on the bottom. So because I have this faster moving area, I have a lower pressure and thus a net force. So this is called the Magnus effect. However, this is not really a satisfactory explanation because we can do this exact same experiment. And if we change the conditions, say we made the ball smoother or change the speeds or something like that, we can actually get the opposite force to occur with the same spin, same free stream, but we can get a force generated in the opposite direction. So the Magnus effect cannot be the explanation. This is a little more subtle, but based on our discussion, we might think that this has to do with boundary layers, and indeed it does. And the idea here is that if we look at this picture we've discussed already, from laminar to turbulent, right, we kind of get this change in the boundary layer behavior. But if you notice in the turbulent case, as I increase in Reynolds number further, that the drag actually goes up. And so if I was to call this my solid, and here's going to be a dashed line over here, just to represent a high Reynolds number, that this wake actually starts getting bigger again as I get to even higher turbulent speeds. So with that in mind, this last picture will kind of explain this. Let's first look on the right. So here's my tennis ball, some underspin. This is the normal condition. The tennis ball, it's all rough, right? It has this fuzziness, which one of my students today told me this is called a nap. So it's fuzzy all over. So that's going to make both sides turbulent, even with a relatively low speed. So because both are turbulent, what happens is that from the perspective of the boundary layer, because I'm rotating, this is actually higher speeds on this side, right? Because I'm rotating into the incoming free stream. So I see higher speeds on this side. So the bottom is actually more over here than over here. So it sees this separation occurring earlier on the sphere. So it occurs up here earlier in the sphere, whereas on the backside where my speed is lower, relatively speaking, from the perspective of if I'm sitting on the ball, right, then this stays attached longer. And so because it does, if we remember on the sphere, right, we have stagnation here and we accelerate over here. I get to my lowest pressure here at the top and then I come back around. Well, because this boundary layer is out of the way, I get the low pressure up here, and thus I get this net force upward. And that matches what the Magnus effect predicts, but that's somewhat, just somewhat coincidental. That's not actually a good explanation because we can get the opposite behavior over here. Now, this is hard to create. This is easier to do in the lab because what happens is I need to create it such that one side is laminar and the other is turbulent. So again, because I'm rotating this, if I'm sitting here on the ball and I'm rotating, I see a faster incoming relative speed on the bottom. So again, I still see higher speeds on the top. So if the conditions are such that that lower speed puts me just in the laminar region and the bottom puts me just in the turbulent region, then the laminar region separates early, the turbulent region separates late, and I get a downward force. So, you know, we could take that tennis ball, if we made it smooth such that we could preserve laminar flow longer and hit it at just the right speed, then we could get this downward force, which is opposite of what we predict. Okay, so that's it for today. Next time we'll get into some of the math of boundary layer equations and how we can measure some of the thicknesses of these boundary layers.